Transformers are the silent architects of our power infrastructure. In a substation, a step-up transformer pushes tens of thousands of volts across hundreds of kilometers. On your street corner, a distribution transformer steps that grid voltage down to a usable level. And in your hand, a charger adapts power for sensitive electronics. We know why we need them. But once we determine the required voltage, how exactly does a transformer achieve precise transformation? Today, we break down the engineering logic. In power systems, the transformer is the core static device for voltage conversion. Its operation is governed by Faraday's law of electromagnetic induction. In an ideal model, the main magnetic flux is perfectly coupled between the primary and secondary windings. The induced electromotive force, or EMF, is directly proportional to the rate of change of magnetic flux and, crucially, the number of turns. So, what is N? N represents the physical number of turns wound on the primary and secondary sides. By comparing the induced EMF on both sides, we derive the fundamental turns ratio equation. U1 over U2 is approximately equal to N1 over N2. Simply put, the voltage ratio equals the turns ratio. Furthermore, based on the law of conservation of energy, assuming negligible losses, input power approximates output power. This dictates that current is inversely proportional to the turns ratio. But here is the engineering reality. The grid is never constant. To achieve precise output in the real world, we cannot rely on a fixed N. So we introduce taps. A tap is a connection point made along a transformer winding that allows a specific number of turns to be selected. By changing the tap position, you effectively alter the turns ratio, which in turn adjusts the output voltage. Let's check this formula. K final equals 1 plus tap K fixed equals 1 plus tap N1 N2. Transformer taps generally do not exceed 5%, so they provide only a fine adjustment to the turns ratio and voltage. There are two critical rules regarding taps that every junior engineer must grasp. Rule 1. Taps are located on the high voltage HV side. Why? Two reasons. First, the HV side has lower current, which reduces the arc and thermal stress on the switch contacts. Second, HV windings are typically wound on the outer layer, making them physically accessible for mechanical connections. Rule 2. The negative logic of regulation. This is counterintuitive. In a standard step-down transformer, the high voltage side is the primary. If you select a positive tap, for example, plus 2.5%, you are adding turns to the primary, which decreases the secondary output voltage. Conversely, a negative tap reduces turns on the primary, thereby increasing the output voltage. Let's verify this with a simulation in a single-phase transformer. First, a step-down scenario. We set the primary to 10 turns and the secondary to 5 turns. This gives us a ratio of 2. With a 220 volts input, the secondary output is precisely 110 volts, matching our formula. By default, the tap position is at 0. For a ratio 2 transformer, selecting a plus 5% tap changes the ratio to 2.1. Consequently, the output voltage drops by roughly 5%. Note that these are RMS, root mean square values. Since AC voltage is a sinusoidal waveform, the instantaneous value fluctuates. On the oscilloscope, we see the real-time waveform. As engineers, we must remember the peak value, about square root of 2 times the RMS value. For a 220 volt system, the peak value is about 311 volts. Now, if we keep the primary constant but increase the secondary to 20 turns, the ratio becomes 0.5. The transformer now operates in step-up mode, outputting 440 volts. Finally, let's look at how we apply this in the field. 1. Rated voltage selection. This must strictly align with nominal system voltages, for example, 66 kilovolts, 11 kilovolts, 11 kilovolts, 0.42 kilovolts. Here is a comparison table showing voltage levels across different national standards. Taking low voltage systems as an example, under China's GB standard, The single-phase voltage is 220 volts, and the three-phase voltage is 380 volts. Under the European IEC standard, the single-phase voltage is 230 volts, and the three-phase voltage is 400 volts. Situation in North America, however, is different and more complex. In summary, the voltage levels under the GB and IEC standards are almost the same, whereas North America is unique, characterized by a wider variety of voltage types and distinct regional differences. So before we decide to design the transformer, we need to consult local standards and grid code. When selecting the rated voltage, I would like to emphasize two key points. The first is the 5% compensation principle. Transformers often have a secondary rating higher than that of the terminal equipment to compensate for line voltage drop. For example, in Europe applied 11 kV 0.42 kV transformer for 400 volts motors. The second is insulation coordination. It's crucial to remember that rated voltage governs the entire insulation system. Tank dimensions, oil volume, and internal clearances are strictly designed according to these insulation requirements. You simply cannot substitute a 66 kV 11 kV transformer with a 660 volts 110 volts unit, just because they share the same ratio. 2. Tap changer types. There are two kinds of types, NLTC and OLTC. The first is NLTC off-load. It's common for distribution transformers under 12 kV. Off-load means the transformer must be de-energized before switching. Standard distribution transformers typically offer a range of plus or minus 5%, usually configured as 5 positions with plus or minus 2.5% steps. The second is OLTC on-load. For 33 kV electrical system and above, on-load tap changers are widely used in the transformer. These systems use transition resistors to switch taps without interrupting power. By offering 17 or more discrete steps, they provide smooth, continuous regulation. Here is a comparison table to help everyone understand the detailed difference between these two types. Simply put, OLTC is suitable for applications where continuity of supply is critical. However, this comes with higher costs and an increased maintenance workload. Before we finish our video, let's move into TechBridge Glossary to recap the high frequency.
Step up. Step up. A transformer where the output voltage is higher than the input voltage. Step down. Step down. A transformer where the output voltage is lower than the input voltage. Turns ratio. Turns ratio. The fundamental fixed design constant of a transformer. The ratio of turns in a primary coil to turns in a secondary coil. It precisely determines the transformer's step-up or step-down function. Tap. Tap. A tap is a connection point made along a transformer winding that allows a specific number of turns to be selected. By changing the tap position, you effectively alter the turns ratio, which in turn adjusts the output voltage.
Now it is time to take a screenshot of the terminology summary. 3, 2, 1. Okay. If you have any questions or want to see specific engineering topics covered, please leave a comment. Don't forget to subscribe to the channel. This is TechBridge. Stay curious, stay professional. See you next time.